In the fully developed region, because of the simplifications in the governing equations that we just saw, we can get an analytical solution. We can integrate the governing equations. And this is valid, and we get an analytical solution that's valid only in the fully developed region. The velocity profile comes out to be parabolic, and it can be written in this form. So on the left-hand side, I have the axial velocity normalized by the average velocity. And on the right-hand side, it's proportional to this r squared. So that's where you get the parabolic. And at r equal to 0, basically the right-hand side reduces to 2. That means over here, the average velocity is twice the axial velocity is twice the average velocity. So in our case, the average velocity is 1. So you have 1 meter per second over there, and then in the fully developed region, it'll be twice that. So it'll just be 2 meters per second. So that's something we can look for in our numerical solution. The analytical solution also gives you the skin friction coefficient, which is a normalized wall shear, and that can be written in this form. So the wall shear, tau W, it's basically giving you the friction at the wall. Okay, that's friction per unit area. And that'll be, in this case, in the fully developed region, it'll be related to the normal gradient, actually. So I should say this is V sub Z. Okay, so that's the gradient of the axial velocity in the radial direction, and we need to evaluate this at the wall. And if we take that, so from the velocity profile, we can differentiate that and calculate that and plug it back here, and then normalize it by half rho v squared, which is the dynamic pressure in the free stream. So this is kind of, you can think of it as a measure of the kinetic energy in the free stream. And when you plug that velocity profile in here and so on, you will get a very simple result. It's 16 over the Reynolds number. And in our case, Reynolds number is 100. So the skin friction coefficient in the fully developed region, we expect to be 0.16. So CF will be equal to 0.16. That's what we expect over here. One thing I wanted to mention is how the hand calculations relate to the mathematical model, because I've seen students, considering the hand calcs to be completely different from the mathematical model that that the Fluent solver is using. What we have done in the analytical solution is we have taken the same mathematical model and we have made additional assumptions in the fully developed region, and we derived an analytical result. So in the hand calcs in the fully developed region, we have the same mathematical model. I'll abbreviate that as just model, and we have additional assumptions. And because of the additional assumptions, we get a closed form solution.